Welcome to lecture 15. In this lecture, I will talk about hydrodynamics. What is hydrodynamics? A formal definition for hydrodynamics is that it is the effective theory of matter at long wavelength. This means that the hydrodynamic formulation is universal. It means that it applies to all systems regardless of their size, as long as the timescales at which one considers the system is very, very long. Examples of hydrodynamic systems include lakes, Earth atmosphere, glasses, which also flow at sufficiently long timescales, rock, such as Earth as a whole, which can be described as a fluid on geological timescales, the sun, which can be described as a fluid that's charged, and the universe, which can also be described as a fluid at very, very long, meaning cosmological timescales. The modern formulation for hydrodynamics uses the tool of effective field theory, or EFT for short, and that's also the approach that will be taken in this lecture. To get started, let us review some of the statements about conservation laws that we talked about in lecture 8. So for example, if we have a conserved charge, then the conserved quantity that is going along with this is the electric forecurrent J mu, which in components consists of the charge density N and the current density J. The conservation law takes the following form. It's the for divergence of the current is equal to 0. And you can remind yourself that this is a conservation law by integrating this equation with respect to some volume V, which is very large. So if we do this on the left-hand side, we can interchange the time derivative and the volume because these don't, because these commute with each other. So this time derivative and the space volume are exchangeable. And on the right-hand side, we then have the volume integral of a divergence of the current density. That is a surface integral. And if you make the volume, the surface bounding the volume very, very large, we can send this to infinity. And then this right-hand term is just a boundary term that we can, that basically goes to 0. So if we define the total charge Q as the volume integral of the charge density, the equation 15.3 reads dtq is 0, and that just means that the charge Q does not change as a function of time because its time derivative is vanishing. Suppose now we want to know how an initial distribution of charge evolves as a function of time. So we are asking a question about the dynamics of the system. So what we have to supply is an initial condition for the charge density. Let's say this is n as a function of space variable x at some initial time t0. And what we would be interested in is this charge density n as a function of space for some later time t. In full generality, this is a very difficult problem to answer, especially if we want to deal with an exact answer in quantum field theory, for instance. However, in many situations, we are actually not that interested in the precise exact solution to this question, but we are perfectly happy to sort of have some approximate answer for how this charge distribution evolves as a function of time, as long as sort of is sort of having some measure of being converging to some exact answer at late times, for instance. So we want to know where the charges end up. In order to get this, we first have to find an equation that lets us describe the time evolution of the charge density. And in order to get that equation, we will use the framework of effective field theory. In the effective field theory framework, what we have to start with is we have to start with effective field theory variables. In our case, we are dealing with the conservation equation for the electric charge. The electric charge is a scalar. So there is a scalar quantity that is a good variable for EFT framework. And the variable that we can take is, for instance, the charge density n. Once we have the EFT variable, we then proceed to construct properties of the theory that we want to describe in terms of a gradient expansion of the variable. This is basically the EFT framework. And for the case at hand, the quantity that we want to sort of construct is we want to have an equation for the time evolution. We have the conservation law that's given in components in this equation 15.5, the time derivative of the charge density plus the divergence of the current density is 0. But what we would like to have is a simple partial differential equation for the charge density n. What we don't know is the current density j. So clearly what we want to construct in our EFT framework is some relation between the current density j and the charge density n. So n here is our variable, so we want to express the current density j in terms of n. Since j is a vector, something like vector j is the gradient of n will work. So we can take vector of j is some function in principle d that can depend on n itself times the gradient of n. And I have introduced a minus sign here, which is pure convention. I could have absorbed it in this function d, but with the minus sign, it turns out that the corresponding equation for our evolution of n will look more familiar. I said that d can be a function, or will in general be a function of n. To minimize the writing, I will from now on just assume that d is constant, simply because the equation that I get is much easier, but there's no reason that one has to sort of make this assumption. If d is a constant and j vector is equal to minus d times the gradient of n, I can plug this into the conservation law. The conservation law is the for divergence of the current density equal to 0, and that just leads to dtn is the gradient squared of n. So now this is a partial differential equation that only depends on n, and as such, this conservation, given an initial condition for n, will dictate the time evolution of the charge density, which is basically the problem that we wanted to solve in the beginning. So this equation is a good equation for telling us what the charge density will do as a function of time. And this is a known equation. This equation has the name of diffusion equation. And as such, it constitutes one particular example for an effective field theory treatment of the dynamics of charge. Note that the diffusion equation is an example of first order hydrodynamics, in the sense that hydrodynamics is just the long time limit that comes out of an EFT framework, in this case for charge. And it is a first order because it is only first order gradients that we allowed in the construction of j. So here we said that j is equal to the first order gradient of n, and that's why it's a first order treatment. In principle, we could have tried something even simpler. We could have tried to do 0th order diffusion. Since there is no 0th order quantity that involves the charge density n that is a vector, 0th order diffusion would have meant that we put j vectors equal to 0. That's a possible choice. If we plug this into the conservation equation, we get that the charge density, the derivative, time derivative of the charge density is just vanishing. And this means that the charge density is constant as a function of time, which is a particular solution for the time evolution of charge density. It's not a very interesting solution. So that's why usually one considers the diffusion equation to be the first non-trivial order at which stuff happens. But in principle, we could have done 0th order diffusion. So while this is not very interesting for the problem of diffusion, I'm pointing this out because when we talk about actual hydrodynamics or the dynamics of fluids, 0th order gradient expansion happens to be an interesting approximation. Let us now ask some questions concerning the diffusion equation that we have derived in this way. We said that the current conservation is exact, so that means that the conservation law that we have in equation 15.11, that doesn't change. So there's nothing in here that is approximate in any sense of the word, as long as we are in flat spacetime. The diffusion equation that we got was an equation that only involved the charge density n and some diffusion constant, in this case d. And we can ask ourselves a number of questions, such as, is the diffusion equation exact? Another question that we could ask is, what system does this diffusion equation actually describe? Does it describe electrons? Does it describe something more exotic like string theory? Does it describe black holes? And finally, we could ask ourselves, how does the microphysics of the system that we want to describe actually enter in the diffusion equation? I will provide some brief answers, in particular to the first part of this equation, namely whether the diffusion equation is exact. The short answer to the question is no. Unlike the conservation for the current that's given in equation 15.11, the diffusion equation we got by truncating the gradient expansion as first order gradients. So clearly that is not an exact statement, it's just an approximation because we neglect all higher order gradients. So the diffusion equation is not an exact equation. It is an approximation to whatever sort of dynamics is there in the system. And that is good because, as I said, the full dynamics is given by this equation here, where J can be a very, very complicated function of n. And the diffusion equation simplifies this down to an equation that is just a simple partial differential equation. So this is very easy to solve. The dynamics for the charge density from this equation, it would be very, very hard to solve. So the fact that we did this approximation makes the problem actually tractable. Also note that I sort of here have used the approximation that the d here is a constant rather than a function. That is another approximation that goes in here. And we will learn another sort of approximation on this equation that will be discussed in the next slide. Before I go there, however, let me try to answer the second question here. What system does the diffusion equation describe? Well, the point is that we have not made any assumptions about what system we are describing in here. We sort of have only input the fact that we have some conservation equation, so there's some sort of charge that's conserved, but we have not said whether these are electrons or charged strings or charged black holes. They could be either of those, and in fact, any of those will be described by the diffusion equation in an appropriate limit. So this is known as universality because in the derivation, we have not used any assumption about the system. This means that the resulting diffusion equation does not know about the system, and it means it applies to all systems. However, clearly, the diffusion of electrons will in general be very, very different from the diffusion that's occurring on a charged black hole or the diffusion that is occurring for charged strings. So the diffusion equation somehow should give us something that is a sensible answer for the system that we want to consider. And obviously that answer will be different when we consider electrons or whether we consider black holes. The way that the diffusion equation knows about whether we're describing electrons or black holes is to the only variable in here that is not specified a priori, and that is this diffusion constant d. So that is the only information about what system we describe. And this also answers the third question that I've put on this slide here. How does the microphysics enter the diffusion equation? Well, it is precisely through the value of this constant d that the microphysics enters into this diffusion equation, and that the microphysics describes what kind of evolution the charge density actually takes. Let me now elaborate a little bit on the answer to the first question, namely, what are possible corrections to the simple first order diffusion equation that I discussed on the last slide. I already mentioned that in order to write down the constitutive relation, meaning the relation between the current density J and the charge density N, in the simple diffusion equation, we truncated this relation at first order, but in principle, there can be higher order correction terms. I've written down another correction term in here. That correction term is now third order ingredients, comes in with a different coefficient alpha, but there's no reason that this has to stop here. So this can go on in principle forever. So there can be very, very high order contributions to this charge density. And then one can wonder whether this gradient expansion actually forms a convergent series or divergent series, asymptotic series, and so on and so forth. This is actually a topic of current research in the field of high energy physics. But for the purpose of this lecture, let me just point out that, okay, there are these higher order gradient correction terms that are in principle there. The second correction or source of corrections that I want to sort of talk about are so-called non-vanishing sources. So what are these? So basically the idea is that if we want to deal with dynamics of charges, we are basically sort of considering a case where we have moving charges, their charge densities, their currents, and as such, at least when we sort of take our familiar concept of electromagnetism, these currents will come along with associated fields. Okay, so basically for moving charges, electromagnetism tells us that there should be electric and magnetic fields. So we expect that our diffusion equation should include corrections that come from the action of these fields. In fact, we can sort of include those in our EFT setup by saying that, okay, let us write down terms that are now proportional not only to gradients of n, but also to the electric and magnetic fields. And the first non-trivial term that we can write down is, for instance, a term that is proportional to the electric field E times another coefficient sigma. I could go on and say why there is no correction coming in from the B field. Basically, I have taciturnly assumed another kind of symmetry, which is known as parity. But let me just point out that, okay, there are in principle corrections to the constitutive equation that involve these electric and magnetic fields. So if we truncate here, so we allow first order gradient terms in the charge density n, and we allow, for instance, the electric field, which, by the way, is also a first order gradient of some underlying potential, gauge potential, then we find that the conservation equation d mu g mu is 0 leads to a kind of modified diffusion equation, which not only involves the diffusion constant, but also involves the divergence of the electric field times this constant here. And that basically sort of is a term that is essentially the ohmic resistance, or some people call this the ohmic resistance terms in the diffusion equation. So this is a term that one expects has to be there, and it just follows naturally from this effective field theory framework. As you can tell, the simple diffusion equation only involves n. This equation here involves the electric field. So you can read this either in two ways. You can say that, okay, there is an external electric field, E, and I want to sort of see what my charge density n does in the presence of this background external electric field E. And then you can go and solve this equation here. Or you can say, oh, really what I'm interested in is I'm interested in the electric field that is generated by my moving charges n themselves, so that's coupled back to my diffusion equation. Then you need to supplement this equation by the field equation that the electric field E fulfills, and that would be the Maxwell equations with the current density that sort of comes out of this. And the corresponding sort of system of equations then involves this equation here together with the Maxwell equations, and this then forms a self-consistent set of equations, which sometimes is called the Vlasov equations, and you can go and solve these. Okay, so the purpose of the previous slides was really just to say that there is this notion of an effective field theory treatment that you can use to set up a an equation that governs the dynamics of the quantities that you're interested in. So for the case that I have set out, I considered a conserved charge. So the good variable for an EFT framework was then the charge density n. Once one has a good variable, one then goes ahead and constructs a constitutive relation for the unknown parts of the equation, such as the current density J, from the gradients of the variable n. And also the associated sources for electromagnetic charges. This would be electric and magnetic fields. Once one has this, plug in the results that you get from this EFT expansion into the conservation law, and out pops an equation for the dynamics that you can use to predict what the, for instance, charge density will evolve to as a function of time. Since this setup doesn't rely on any specific microscopic details, it only relies on symmetries. The resulting equation that you get is valid not only for one particular system, but it's universally true. So you get a universal equation that describes a whole class of systems, or basically every system in a certain limit, every system that has a conserved charge in a certain limit. And the sort of, if you want to, the price to pay is that while the form of the equation is universal, the coefficients, such as the diffusion constant d, will be the ones that depend on the specific system, will depend on the microphysics that you're trying to describe. If you are sort of looking for more details than just these brief sort of introduction into the effective field theory treatment of hydrodynamics, I wrote a whole book about this. So please have a look by clicking at this link at the full text version of the book. Yeah, let me know if there are some more detailed questions that you have for this setup. Judging ahead, let us now generalize these ideas of hydrodynamics as an effective field theory by now considering a different set of conservation laws, not electric charge, but energy and momentum. So energy and momentum are also conserved. We have learned that the corresponding conservation law is that of rank 2 tensor, the energy momentum tensor, T mu nu, fulfilling the following equation, equation 15.16. And we would maybe be interested in sort of how the dynamics of these energy momentum conservation sort of boils out. Let's say if we want to say, okay, we have energy distributed in our universe at certain points. How does this energy density evolve as a function of time? In order to do this, well, again, the exact answer to this question is very, very hard to find, but we can get an sort of approximate answer that will be valid at very, very long time scales and very, very sort of large volumes from the framework of effective field theory. Let's do this now. So in order to construct the energy momentum T mu nu from an EFT framework, we first need to figure out the good variables for the effective field theory. To do this, recall that we are interested in energy momentum conservation. So we can think of a four momentum P mu, which combines the energy and the momentum into a four momentum. If we have a four momentum P mu, the four momentum will fulfill some sort of relation, such as the invariant mass squared. So P mu is minus m squared, which is an example that we talked about when we were reviewing special relativity in the early parts of this course. Now, while it's perfectly possible to construct an energy momentum tensor from this four momentum, historically, what people have chosen to do is separate the four momentum density, if you want so, into two parts. The absolute value, so the dimensionful parts of this, which, okay, for instance, would come in as dimension of mass or mass dimension of energy. So we take out this dimensionful scalar here and we call it energy density. And then what we have left is a four vector that is dimensionless, which nevertheless fulfills some sort of relation like this. So long story short, for energy momentum conservation, we can use good EFT variables if we, for instance, use the energy density epsilon and another 4-vector u mu, that nevertheless has to have one more condition, that it's normalized, for instance, such as u mu is -1. The normalization here sort of is such that, okay, this means that we are effectively trying to describe matter. In principle, we could try to do something similar for stuff that is light-like, so fields or so, then u mu would be 0, but that's sort of more exotic treatments. For the point here, for the lecture here, basically, what we are trying to do is come up with an expression for the energy momentum tensor of matter, okay, so ordinary matter. So once we have identified the good variables for the EFT framework, we are now tasked with writing down a gradient expansion for T mu in terms of these fields or these variables epsilon and u mu. Just as with the case of the conserved charges, we should also think about considering sources. So they are an analog of electric and magnetic field for charged particles. So we said that for moving charges, which create electromagnetic fields, we should include the electromagnetic fields in the description. So here what we have now is moving masses, moving energy density, moving masses. So basically the upshot is that we expect that will be associated gravitational fields that get generated from these moving objects. So we should supplement the metric tensor G mu as well as its gradients as possible source terms for the energy momentum tensor. Okay, so now we have our building blocks. We have epsilon, u mu, and the metric tensor. We can now proceed down to write down the contribution to T mu in terms of these. So basically the simplest thing we could do is start by writing down all the terms that do not have any gradients of these. So this is 0th order gradients. So remember, for the diffusion equation, this gave us a result which was not very interesting, but here we have something that will turn out to be interesting. So let's just start at 0th order gradients, so no gradients. What we have is a rank 2 metric tensor. Clearly, that can be a good contribution to T mu if we have some coefficient z0 that in principle can be a function of the energy density epsilon. And in addition, because T mu is supposed to be a symmetric rank 2 tensor, we can use the quantity u mu to build another rank 2 symmetric contribution, namely u mu u nu. And this second contribution can also come in with a function c1 of the energy density epsilon. And if we limit ourselves to lowest order gradients, those are the only two terms that we can write down for a symmetric rank 2 tensor. We cannot write down something that is epsilon times u mu because that only would have one index. We could build more complicated structures if we also would allow gradients of these, but the lowest order gradients, that's the only term that we can write down. So we have these two unknown functions, but the rest of the structure is fixed by the symmetries. In order to fix these two functions now, what we want to do is we want to consider a particular choice for this vector u mu that nevertheless fulfills u mu is -1. And one particular choice for this vector is the so-called local restrain. So think of u mu as being some sort of fluid for velocity, okay? So then there's one particular frame where the matter is at rest, and that is the frame where the fluid velocity is just such that the space part of this is just 0, and that will be a particular nice frame for evaluating our energy momentum tensor. In Minkowski spacetime, where the metric tensor G mu is just the Minkowski metric, then we can write down the energy momentum tensor T mu in the local rest frame LRF, and that is just a diagonal matrix. And the diagonal matrix has the entries -c0 plus z1 in the 0, 0 component, and z0 in the 1, 1, 2, 2, and 3, 3, or x, x, y, y in z components. Now recall that the 0, 0 component of the energy momentum tensor is nothing else but the Hamiltonian density. So what we expect, or we expect then that the combination of the 0, 0 component, which is just minus C0 plus C1, has to be equal to the expectation value of the Hamiltonian density, which is nothing else but the energy density epsilon. So we get one condition for these two functions, C0 and C1. To actually calculate the two functions, Z0 and Z1, we need one more condition. That condition is something that we have not talked about before. You need to basically have a little bit of background in finite temperature quantum field theory or other sort of statistical mechanics problems to know this. But let me just tell you that the space-like part of the energy momentum tensor, so for instance, the XX component or YY component or ZZ component, is just equal to the pressure, P, okay? So that is the second relation that we need, because then we can figure out that this function Z naught is just the pressure P, and the pressure P, of course, is related to the energy density epsilon via the so-called equation of state. So P is a function of epsilon, and the equation of state is something that can be calculated for any statistical mechanics system. So using this, we then have that Z naught is just P, C1 is just from this relation epsilon plus P, so that we find that the energy momentum tensor is uniquely specified in terms of the following structure, equation 15.20. Okay, so this is our energy momentum tensor, the 0th order ingredients, also 0th order hydrodynamics, that's the same thing. The conservation equation for the energy momentum tensor in Minkowski space looks like this. It's the gradient of T mu is 0. And since we now have all the building blocks here, we get 4 equations which describe the evolution of the energy density and the 4 velocity for this particular sort of system. And it turns out you can show that these 4 equations here are nothing else but the so-called Euler equation of fluid dynamics. So Euler equations are something that you might have heard before. Normally, these are equations that describe the dynamics of non-relativistic fluids. Here they come out as a sort of universal description in the relativistic system that then will describe the evolution of matter in an arbitrary sort of setup. Because again, we have not used any particular assumptions about what systems we are actually describing, the form of the energy momentum tensor here is universal, and as such that it applies equally well to lakes in the non-relativistic limit, as well as to the universe, which is much more to the core problem of the course at hand. The only input that tells you whether we're describing water or whether we're describing the universe will be this relation P as a function of epsilon, the equation of state. So that's the only input that will sort of distinguish the outcome of this evolution that will tell you, okay, we are really describing a river or a lake, or whether we're describing a neutron star, or whether we are describing the expansion of the universe. And that's basically sort of the beauty of it, because the setup of the energy momentum tensor is universal, and all the sort of interesting information condenses into this one function that knows about what systems it is that you're describing. So with that, I will stop the present lecture, and we'll, in the future lectures, we will sort of use, in particular, this form of this energy momentum tensor to do interesting things like cosmology.